So this is the circuit that we're going to set up today. As you can see, we have a battery as our power source, we have a light bulb with a switch on the side, and the light bulb is in parallel with a bunch of capacitors. So capacitor A is in a series with capacitor B and C, and capacitor B and C are in parallel with each other. So the goal of our experiment is to find out the charge distribution on the different capacitors within this circuit. After the capacitors are charged, if we disconnect them from the power source and close the switch next to the light bulb, we're going to see that the light bulb lights up because the capacitors are going to discharge through the light bulb. And after a while, the light bulb will go dark again. So the amount of time taken for each capacitor to discharge is going to be related to the amount of charge on that specific capacitor. By hooking up each capacitor to the light bulb individually and measure the time it takes for the light bulb to go dark, we can determine qualitatively how much charge there is on each capacitor in this circuit. For example, if we want to find out the amount of charge on capacitor A in this circuit, we charge it for 30 seconds and then we disconnect the circuit from the power source and we just hook up capacitor A to the light bulb individually. And now we close the switch. So this circuit would enable us to measure the amount of charge on A through the time taken for it to be discharged by measuring the time taken for the light bulb to go dark. We did some calculation to find out the exact amount of charge on each capacitor so that we can predict the time taken for each of them to discharge. First of all, we calculated the equivalent capacitance in this entire circuit by considering that A and the group of B and C are in series and B and C are in parallel. And then we try to calculate the total amount of charge going through the circuit using the equation that Q is equal to the potential difference times the equivalent capacitance. And the potential difference is just the voltage of the battery, which is 3 volts. The amount of charge going through A should be equal to the total amount of charge because A is in a series with the combination of B and C. So the charge on A is also 1.1 coulombs. And the amount of charge going through B and C should also be 1.1 coulombs. This way we can find out the potential difference for B and for C, which are equal because they're in parallel, and the potential difference is about 0.75 volts. Now, knowing the potential difference for B and the capacitance of B, we can calculate the amount of charge on B, which is 0.75 coulombs. Similarly, we can calculate the amount of charge on C, which is 0.35 coulombs. Based on our calculation, the amount of charge on capacitor A is the largest, followed by B, and the amount of charge on capacitor C is the smallest. So we predict that A takes the longest to discharge and C takes the shortest. So now we have the circuit set up. So this is the capacitor A, and it is in a series with capacitor B and C, which are in parallel. And we have a light bulb over here, and they're connected to two 1.5 volts batteries that have a total of 3 volts. And right now the circuit is disconnected, and everything has been discharged because the capacitors are not lighting up the bulb. Okay, so now we're going to charge the capacitors by connecting the yellow wire. And we're going to charge them for 30 seconds to make sure they're fully charged. To discharge all three capacitors by disconnecting them from the batteries and connecting them to the light bulb. And we're trying to see how long it would take for the light bulb to go dark. So it took about 7 to 8 seconds in total. So now we are charging all of the capacitors again for 30 seconds. So now all of the capacitors are charged, and we're going to see how long it takes capacitor A specifically to get discharged by hooking it up to the light bulb and by disconnecting the other two capacitors from the circuit. It took about 7 seconds for capacitor A to discharge. So now we're going to discharge all of the capacitors by turning on the light bulb. And we're going to charge them again for 30 seconds for our next experiment. So again, all of the capacitors are charged, and we're going to see how long specifically does it take for capacitor B to discharge through the light bulb. So we're going to disconnect capacitor A and C from the circuits and hook capacitor B up with the light bulb. So now, if we turn on the switch for the light bulb, we're going to see it lights up. And it takes about 5 seconds for capacitor B to discharge. So we're going to discharge all of them again. And charge all of them for 30 seconds. So now we want to see how long it takes for capacitor C to discharge through the light bulb. We're going to disconnect this capacitor A and B from the circuits and hook capacitor C up with the light bulb. So now when we turn on the light bulb, we're going to see it lights up. Very dim. And it took only 2 seconds for this light bulb to go dim. So the voltage across capacitor A is around 1.63. The potential difference for capacitor B is around 1.48. And the potential difference for capacitor C is around 1.47. According to our previous calculation, the amount of charge on A is 1.1 coulombs, based on the knowledge that capacitor A has a capacitance of 0.47 farads. The voltage across A should be 2.3 volts. And we've also calculated that the voltage across B or that across C should be 0.75 volts. So our calculation does make sense because the potential difference across A and the potential difference across B or C do add up to a total of 3 volts, which is the voltage generated by the battery. So we are really puzzled why our calculation does not match with the results that we observed from the circuit.